So welcome to our second lecture, dealing with galvanic cells. A voltaic cell, or galvanic cell, has three parts: an anode, a cathode, and a salt bridge to keep the charges neutral. The anode attracts anions, the electrons are leaving that electrode going into the wire, and of course the loss of electrons is oxidation. At the cathode attracts cations. The electrons are arriving at this electrode through the wire, and we are getting a reduction taking place. In the shorthand, you start out writing the anode on the far left. You then proceed through the cell using a single vertical line to indicate a change of phase, a double vertical line to indicate the salt bridge, and finally coming out at the far right with the cathode. So let's look at an actual working cell. On the left we have a silver solution, on the right a copper solution. We have an electrode of silver and an electrode of copper with a wire in between them and a salt bridge to keep things neutral. The potential of the cell is the reduction potential plus the oxidation potential. The reduction potential for the silver ions plus 0.80 volts. The reduction potential for the copper ions plus 0.34 volts. So which one runs? Well, basically it's simple. The more positive potential will run as written, and therefore it is the silver reaction that will run as written. That means, of course, that the copper reaction has to be running backwards. So our reactants would have to be the silver ions and the copper solid. That gives us the products of the copper ions and solid silver. So the reduction potential is the 0.80 volts for the silver. The oxidation potential is the 0.34 volts for the copper, but we have to reverse the sign since the copper reaction is running backwards. And so we get the potential for the cell is plus 0.46 volts. But wait a minute, we forgot to balance the equation. The copper atoms are losing 2 electrons. They got to go somewhere. The silver's only picking up 1, so we're going to have 2 silver ions be reduced for every copper atom oxidized. What's that going to do to our potential? And the answer, of course, is nothing. You have to keep in mind what's actually going on here. The copper atoms are losing 2 electrons, and where are the electrons going? They're going into the wire. Do the electrons know what's going to happen at the other end of the wire? No, they're going to reduce something, but they don't know what it is. The potential is the driving force, what's stuffing the electrons into the wire. And it doesn't matter what the reaction is as far as the electrons are concerned. They're only aware of the driving force. And so no, the cell potential does not depend on the stoichiometry. It's simply a difference in desire for the ions and the atoms to gain or lose the electrons. It doesn't matter how many they are doing. So let's consider some other ones. A copper solution with a copper electrode, a lead solution with electrode. What is this going to be? Well, we have to go to our little redox table and look up the appropriate copper and lead potentials. The copper potential plus 0.34 volts. The lead's potential minus 0.13 volts. The reaction will run in the direction of the more positive potential, so that's the copper. So the copper potential will be running forward. That means the lead will be running in reverse. The book and various other tests take the attitude that it's the reduction potential minus the oxidation potential, and in that case, you simply take the potential straight off the sheet. I prefer you pay attention and think about what is actually happening. The reduction potential is running forward, the oxidation potential is being run backwards, and so you have to reverse the sign on it. I don't care which way you learn how to do it, just make sure you're doing it right. So the copper plus 3.34, the lead going backwards plus 1.3, and so the potential for that cell is 0.47 volts. How about lead and nickel? Well, the nickel's potential, minus 0.25. So which one reaction is going to run? Well, the lead at minus 0.13 is more positive than the 0.25. So in fact, the lead is going to be running as written, and it is the nickel that is going to be running backwards. And so the lead minus 0.35, the nickel running backwards becomes plus 0.25, and so the potential for that cell would be plus 1.2 volts. And so we can generate electric currents running through the wire as the electrons move from the anode to the cathode. The nice thing is we can put stuff in their way. That is, we can make the electron current flow do work. So what kind of work are we going to get out of our cell? So we can get work. Well, work requires force and something moving because of the force. Well, the force we're getting, of course, is just simply the electromotive force, that is the epsilon of the cell, the potential difference. And what's moving because of it? Well, the electrons are moving. And so what's moving is the charge. So what is the charge on a mole of electrons? Well, Avogadro's number, 6.022 times 10 to the 23rd. The charge on an electron, 1.602 times 10 to the minus 19th coulombs, gives us what is known as a Faraday. The charge on 1 mole of electrons, 96,487 coulombs. And so we have the epsilon, that's the driving force, the EMF. A Faraday, the charge on 1 mole of electrons, 96,487 coulombs, and N, the number of electrons actually being transferred. And that would give us the amount of work. But the thing to keep in mind, of course, is if you have a positive cell potential, all of that's going to be positive, and the cell's going to be doing work. But work by the system is a loss of energy. So we have to include the minus sign in front of our NF epsilon when we're talking about work by the cell. Well, coulombs times volts is the amount of energy we're getting out. And so what quantity is volt coulombs? Well, it turns out that a volt coulomb is equal to 1 joule of work. And so, how much work could we get out of a cell? For example, a zinc and chromium cell. Well, the reduction potential for the zinc, minus 0.76 volts. The reduction potential for the chromium 3, minus 0.41 volts. Since the chromium is more positive, that is the one that is going to run in the correct direction. So the chromium plus 3 is going to be one of our reactants. The zinc's going to be running backwards. So our other reactant is going to be the zinc metal, and the products are going to be zinc ions and chromium metal. The potential for the chromium is running forward, minus 0.41 volts. The oxidation potential of the zinc is the minus 0.76 volts with the sign reversed because it's running backwards. So the cell would have a potential of 0.35 volts. We have to balance the equation, of course. The zinc is losing 2 electrons. The chromium plus 3s are gaining 3. The first number that includes both 2 and 3, of course, is 6. So we're going to have 3 zinc atoms and 2 chromium ions to give us 3 zinc ions and 2 chromium atoms. So it's a 6 electron transfer. A Faraday, 96,487 coulombs. The potential 0.35, so we're getting 202,622.7 volt coulombs, or in other words, 2.02 202.6 kilojoules of work is possible. But when we were talking thermodynamics, we said the amount of work you can get out of the system is delta G. And therefore, delta G must be equal to minus N Faraday's epsilon, where epsilon is the potential of the cell. But that's under any conditions. Delta G0 is under very specific conditions, and that is what we have for epsilon 0. So the delta G0 is equal to minus NF epsilon 0. Well, we said the relationship between delta G and delta G0 is delta G equals delta G0 plus RT log Q, where Q is the concentration of the reactants and products. And so we can replace the delta G's with NF epsilon. And we in that equation, then divide both sides by NF, the number of electrons transferred, and we get the cell potential is equal to the epsilon 0 minus RT over NF log Q. Well, if we're talking 25 degrees, then RT and F, as well as the log, are all constants, and we can simply pull them all together into one constant, and we find that the epsilon of the cell is epsilon 0 minus 0.00591 volts divided by N, the number of electrons transferred, and now we have the log base 10 for Q. And this is what is known as the Nernst equation. And it allows us to calculate the potential of the cell as the cell runs down from the epsilon 0. So what would be the EMF of the following cell as written? Well, first off, we have to decide who's the anode and who's the cathode, that is, which way the electrons are running. Copper reduction potential, 0.34 volts. The lead's reduction potential, minus 0.13 volts, so the copper is running as written. So the copper ions are reacting with the lead atoms to give us copper atoms and lead ions. The potential for the cell, 0.47 volts. So, cell potential, 0.47 volts minus 0.0591 divided by 2. It's a 2 electron transfer. The log of the products, copper ions and lead ions, divided by copper ions and lead. Have to put in the appropriate numbers. 1 times 0.5 divided by 0.01 times 1 gives us 50. The log of 50, 1.6987. So the potential for the cell is 0.42. And this is what you would expect. We are running out of the reactants, that is the copper plus 2 has gone down in concentration. The amount of lead ions rather has been going up. So we'd expect the cell to in fact have less potential as it runs. And the reaction will run until delta G is 0, which means when the potential of the cell is 0. And when does the potential of the cell become 0? Well, obviously when it reaches equilibrium. So what would be the equilibrium constant for our cell? How far will it run before it actually comes to a stop? So, 0. Potential of the cell at equilibrium, 0.47 volts, the epsilon 0, minus 0.0591 divided by 2, log of K. So the log of K is 0.47 times 2 divided by 0.0591, which is 15.905. So K is 10 to the 15.905. So the equilibrium constant for this reaction would be 8.0 times 10 to the 15th. And so we have another way of getting delta G's, delta D0s, and equilibrium constants. We can simply measure cell potentials and do the necessary calculations to get all those other values. And that brings us to the end of today's lecture on voltaic cells.